Hello and welcome to Minecraft Math Computers, episode I16, where we are talking about the binary number system. We built a great big binary display over here in the last couple of episodes, and you can see that I've extended something on the top here that I'll show you in a little bit. Now, each of these, if you remember, is I can press a button here, and it will change each of these and toggle them back between 0 and 1, or on and off. So I'm going to set these all to 0 to start with. This, and we're going to talk about what the binary number system is. It is actually base 2 numbers. And by base we mean the number of symbols that you use to record your numbers. And I think it'll be easier to come up here and describe a little bit what we understand better, which is our normal numbers, which are base 10. Now the base determines the number of symbols that you use to represent numbers. So I've got the numbers, or the symbols that we use, which we call numbers. I'm going to show them here along the top. Of course, the ones we are familiar with are 0 and 1, 2, 3, 4, 5, 6, 7, 8, and 9. Those are all the symbols we use for our base 10 number. And if, of course, you count them, starting with 0 through 9, you actually have 10 symbols. Now these particular displays that I have set here, these don't use logic gates, they're mechanical. I'll flip back here real quick. You can see that they're using pistons and things like that, cauldrons and a whole bunch of stuff to make this work. But when I click this button, you'll see that each of these will go up. It simply goes to the next number. I don't have a choice to reset it or anything like that. But if you go through our digits, these are all the symbols that I have along the top. They're all right here. Of course, these are our standard counting numbers. And as in increment 1, we go through our numbers until we get to here. Here, we do something different. We put this back to 0, which is our first number, and we change this one over here to the first symbol that is non-zero. And that's how we arrive at 10. So with a base number, a base 10 number, this represents the first of the symbols. We go through all the symbols, 0 through 9. When we reach 9, we go back to the first symbol, and we go one space to the left, and we go to the next symbol there, which is 1. And that's how base 10 works. The reason it's called base 10 is because of those 10 symbols, and that also means a couple of other things. Now this number here, on the very far right, we call the ones. This number we call the tens. This number would be the hundreds. The next one would be the thousands, the 10,000s, the 100,000s, etc. Each time we move left in this direction, we're taking the number times 10. If we start with 1, we take it times 10, we get 10, we take 10 times 10, we get 100. We're just simply adding a 0 on the end and shifting them all to the left. That's base 10. Now what this actually means is, I'm going to back here, and get a little space up here, we're going to talk about the math behind this. So this number is actually 10 to the 0th power, because this is exponential. We'll see how this works. Each time we advance by a power of the base. So this is 10 to the 0. Any number to the 0 is actually 1. That's how it works. 2 to the 0, 1. 3 to the 0, 1. 4 to the 0, 100 to the 0. Doesn't matter. They're all equal to 1. We're going to label this right here with a sign that says 10. That's going to be our to the power of 0. And we call this the ones. This next one, however, is actually, you take your base and you take it to the next power up, which is 10 to the 1. So this becomes 10 to the 1, and we call that tens. And this last one that I have recorded here would be then 10 to the 2. 10 to the 2, which is 10 times 10, which is 100. We call that hundreds. And that is exactly why we do that. In 3 digits, we have ones, tens, and hundreds. That is 10 to the 0, 10 to the 1, and 10 to the 2. Now I'm going to put another number here. I'm just going to advance this one a couple as well. We'll go maybe to 3. So there's 22. I'm going to make it 23 so that we can see it. So what this is saying is, this is a number. Back up here, we're going to work along the top again. That this number, this particular position here, is 10 to the 0 times this symbol, which is 3. 1, 2, 3. So we end up with 3. This, however, is 10 to the 1, which is 10, times this symbol, which is 2. So 10 to the 1, 10 times 2 is 20. So this number becomes 23. If I were to advance this one, and that one, we have 44. Let me make that just 45. So now we have 10 to the 0 times 5, which is 5. And we have also 10 to the 1, which is 10, times 4, which is 40. So 40 plus 5 equals 45. And we can carry on over here. I can actually add a number here. I'll put on 2. And now we have 245. Same as we had before. This is 10 to the 0, which is 1 times 5 is 5. 10 to the 1 times 4, which is 10 times 4 is 40. And then over here we have 10 to the 2, which is 10 times 10, which is 100, which is then times 2. So it's 2 times 100 plus 4 times 10 plus 5 is 245. So that's how base 10 numbers work. If I had another one over here, of course it would be 10 to the 3. That would be 1,000 because it would be 10 times 10 is 100 times 10 is 1,000. So every time I move one from the right to the left, I'm actually going to the next power of the base, which is 10. So that's how base 10 numbers work. It doesn't matter. Let me just get this button back here. And we're going to put something on this one. Something on this one, maybe. You won't see what it is. There, there, and there. So now we have what we would call 478. 10 to the 0, which is 1 times 8, is 8. 10 to the 1, which is 10 times 7, is 70. 10 to the 2, which is 100 times 4, is 400. 400 plus 70 plus 8 is 478. That's an easy way to do that. Now let me get these advanced forward. We're going to go back to 0 for all of these. And that will take just a second. So when we start counting by 10, we start with 0. You always start with 0 because you have none. You count the first one, which becomes 1. And then 2, 3, 4, 5, 6, 7, 8, 9. Now when you get to 9, that's when you run out of symbols in base 10 because we only have 10 symbols. And so we turn this back to a 0 and we move over here in a 1. So this is basically saying how many 10s are there in 10. There is 1 10 and 0 ones, and of course 0 hundreds. And then we simply start counting again until we achieve our 9 again. We'll get there quickly. So here we are at 19. We've gone through all 10 symbols on this side again. So when we advance one more, we advance that to 0, and we advance this to 2. That says there's now 2 10s and no 1s. And that's how base 10 works. Okay, so now we're going to talk about base 2. Binary is simply base 2. So the only symbols we have in binary are 0 and 1. That is 2 symbols. We've already seen them. I can press this button, we get 0 and 1. And just like we did with the base 10 up here, I'm going to put down a sign. Over on, actually I think I'll just get rid of these and I'll replace them. So this is 2 to the 0, which is 1. That indicates this digit over here. This, just like it says there, is then 2 to the 1. And so forth. Now you may not be familiar with these because before we're simply counting by 10s. 2 to the 0 is actually, as we talked about before, simply 1. 2 to the 1, that's pretty simple. Anything to 1 power is itself, is 2. 2 to the 2 is 2 times 2, which is 4. This is 2 to the 3, which is 2 times 2 times 2, which is 8, and so forth. 2 to the 4, 16. 2 to the 5, 32. 2 to the 6, 64. And finally, 2 to the 7 is 128. So just like up here with base 10, where we said that this number is this number times 10 times 10, we do the same thing here. It's 2 times 2 times 2 times 2 all the way through. And so what those numbers give us are 1, 2, 4, 8, 16, 32, 64, 128. The next would be 256, then 512, then 1024, then 248, 4096, and so forth. Now when you're talking about an 8-bit computer, or 8 bits, this is exactly what you have. You have 8 different bits in a byte, and a byte then is the smallest representation of data that you have. In a 4-bit computer, what would you have? You'd be 1, 2, 3, and 4. The way these work is just like up here. We add this number, which is 20, plus that number, which is 0. In this case, it's not as obvious to us because we're used to base 10, but we simply add them up. This is 0 or 1. This then makes it 2 or 3. And then this can go from there. So let's talk about exactly how binary would work. Up here on our display right now, we have a 0. As soon as I click that, we get a 1. So that is 2 to the 0, which is always 0, remember? Any number to the 0 is 1, so we're there. It's good. Just like here, when we ran out of symbols, we've used 0 and 1 already. I have to reset this one and move to the next one. So here we have now 2 to the 0, which is 1. We don't have any 1. How many 2's do we have? We have 1, 2. So that is 2 plus 0, which is 2. Now I've ran out of symbols here, but I come back here. So just as we're counting up into here, when I moved 1 to here and went back to 0, I went all the way up to 9, and then I moved this and I moved this back to 0. So I start over here, and I add this one again. So that now says we have 2 to the 0, which is 1, times 1. And here we have 2 to the first, which is 2. So add these together and you end up with 3. So that is 3. Of course, if we want to add 1, these have already run out. So we reset that one, we reset that one, and we add it here. And that is, of course, 4. It says it is 2 to the 2, which is 4, plus 0 2's plus 0 1's, so 4. Add 1 to it, you get 5. So that is 5 items in binary. And of course, we have to flip this back, and then this to get to the next number. That is 6 because it is 4 plus 2, and then the last one is 7. So binary is very easy to see because you just go back and forth. So you set this, you toggle this between 0 and 1, and then you add a 1 to here, that becomes a 0. You toggle it again, and then you have a 1, and so forth. So as we're counting up here, I'm going to reset all these, and I'll go through them relatively quickly. So there is our first number, 0, then a 1. We have to toggle this one, set this one. That is 2, 3. Turn these both off, move over here. I'm going to go through these quickly now. When you arrive here for the first time, you are at 8. So that means, if you want to know how many numbers or what's the highest you can count in 4 bits, it is 8. Plus 4, plus 2, plus 1. So 0 through 15. 0, right? So you have 8 plus 4 is 12. 12 plus 2 is 14, and 1 is 15. So you have 16 different numbers, including 0, you can represent with 4 bits. So a 4-bit computer could do that at the most. Right here we are at 8. We go forward again. That is 8, 9, 10, 11, 12. So here we are at 12. You have 8 plus 4. That is 2 to the third plus 2 to the second, which is 8 plus 4. So that's 12. 13. 14. And 15. The 4 right-hand bits all set is equal to 15. If we move forward and we add one more, that means we have to clear all of these and toggle that one. Which is 2 to the 4th, which you can see right down here is 16. So that is the number 16. Then we go all the way back here and we go through that same pattern again. 17. 18. 19. 20. 21. 22. 23. 24. 25. 26. 27. 28. 29. 30. 31. Here we are at 31. That is 16 plus 8 plus 4 plus 2 plus 1. If we add one more, we shift all of these over. Our next number is going to be, of course, from 31 to 32. So I would clear all of these. And that is 32. That is 2 to the 5th times 1, which is 32, with nothing else added in but a bunch of zeros, 32. As soon as I come over here and add 1, we go to 33. 34. 'Okay, so now we're back to 0. One thing you'll notice very easily and very quickly is to find odd or even in binary is very simple, because this can only represent 1. So odd numbers have a 1 in the far right position, and even numbers have a 0. Now something very easy is to figure out odd and even. That's an even number, that's an odd. So no matter what you have here, it doesn't matter. To find out even or odd in binary, if that is a 1, it is even. In other words, if it's a 1. Of course, it's a lot harder to do in base 10. You got to find out if it's divisible by 2 and things like that. So very large numbers, you have to decide, does it end in 2, does it end in 4, 6, 8, or 0? Then it is actually even. But here it's very simple. Look at the last digit. If it's a 1, it's odd. If it's a 0, even. So that is base 2, or what we call binary numbers. So let's just do a quick test. I'm going to put a number in here. We'll see what its value is. There it is. We know that this number is actually odd because there's a 1 there. So that means there's a 1, so we know it's odd. But what we would do to figure this out is we start over here with this digit right here. We want to look at our sheet, and it tells us that 2 to the 6th is 64. So that is 64. The next one would be 32, which we have no 32s. We have 164, no 32s. We have 116. We have no 8s. We have a 4, and we have a 1. So you simply find your number. You can add all of these up. So it's 64 plus 16, which is 80, plus 4, which is 84, plus 1, 85. So what you're looking at here in binary is 85. What I'm going to do is put that up here. So there you have 85 in base 10 at the top and binary at the bottom. I'm going to set another number for another test. Let's put a number on this one. At the top, we have 139 as our number. What is that in binary? We start on this side. There's a couple ways to do this, but the easiest way is we're going to look here and say, is it greater than 128? Yes. So we turn that on. And what that means is we now have a 128. So we would then have to calculate 139 minus 128. And of course, what do you get? You get 11. 64 is larger than 11, so we skip it. 32 is larger than 11, we skip it. 16 larger than 11. 8 is smaller, so we turn on an 8. 11 minus 8 is 3, which is 4 is larger than 3, so we can't have it. And then we add a 2. 3 minus 2 is 1, and so we need our 1. So here's the equivalent of two numbers. 139 in base 10 is 1, 0, 0, 0, 1, 0, 1, 1 in binary. Let's do one more. $102 in base 10. Let's clear our binary and start over. By the same process, you could say that 128 is larger than 103, but we have a 64. So then you have to calculate what is 1 up here. 102 minus 64. Of course, the answer is 38. 38 is, 64 is larger than 38, but we do have a 32. So we turn that on. 38 minus 32 is a 6, which means 16 is too large, 8 is too large, 4 is not. And of course, 4 plus 2 right here is what we wanted, 6. So there we are. 102 in base 10 is 1, 1, 0, 0, 1, 1, 0 in binary. So that is the binary number system, or base 2. I'm going to do one last test, and we'll put a number on here. What is this number in base 10? How do you calculate it? It is 10 to the 7th, 128. 2 to the 4th, which is 16. 2 to the 3rd, which is 8. And then, of course, 2 to the 1, it's 2. If you add all that up, you end up with the number 144. So there you have it. 1001, 1010, or if you want to think of that as on, off, off, on, off, or powered, no power, no power, powered, powered, no power, powered, no power, is the same as 144 in base 10. Short and simple today. Binary might seem confusing, but if you think about it just like this, it's the power of 2's. Just like we do the power of 10's up here. It seems a little odd because since we only have 2 symbols, that means as soon as we use the symbol, get this back to 0. Now, the other interesting thing about binary is up here, if we take a number and we put it on, such as 4, and we take it times the base, you get 40. So you just put a 0 on the end, correct? If then you take that 40 and you take it times 10, you shift it one more to the left and put a 0 on the end, you get 400. Well, it's exactly the same thing with binary. If I shift this one bit this way, it's equivalent of taking it times 2, which is the base. Take this times 10, which is the base. You move everything to the left and add a 0. Take this times 2, which is the base. Same thing. So now we're at 4. Eight. Of course, 8 times 2. 16. 16 times 2, 32. Same thing. So if we shift 1 to the left, we take it times 2. Obviously, if we go backwards, 32 this way would be division by 2. So we divide by 2, 32 divided by 2. 16. 16 divided by 2 is 8. 8 divided by 2 is 4. Just like up here, 144 divided by 10 would be 14. 14 divided by 10 would be 1. It keeps shifting this way, and you lose the last digit. That is the end of I16, binary numbers. Hope you got it. Hope you get it. Binary numbers are pretty amazing stuff. We're going to be using them all through the rest of the immediate series as we build an 8-bit computer. Hang in there. Hope you're learning. This is Imroy, out.